What happens when the funding for your research disappears overnight and shortly after you receive one of the most prestigious awards in the world? For Lauren Williams, professor of mathematics at Harvard University and a 2025 MacArthur Fellow, that wasn't a thought experiment. In the span of a few months, federal grants supporting her work were suddenly canceled. Conferences were thrown into chaos. The future of research funding felt uncertain. And then she was awarded the MacArthur Fellowship, often called the Genius Grant. But the story doesn't stop there. Lauren Williams is one of the leading voices in algebraic combinatorics, a field that studies the deep structure of discrete systems, ideas that quietly connect geometry, physics, probability, and even things like traffic flow and protein synthesis. She's also helping lead one of the most fascinating experiments happening in mathematics today, testing whether artificial intelligence can actually produce mathematical proofs. Today, we're pulling back the curtain on what mathematical research really looks like. The discoveries, the surprises, the collaborations, and even the moments when a math paper and a baby are born the same week. Before we begin, the views shared in this conversation are Lauren's own and do not necessarily reflect the views of her employer or any institution she works with or is affiliated with. So let's begin. I'm Autumn Fineff, and I'm joined by my co-host, Noah John Siracusa, and this is Breaking Math.
Okay, Lauren, so back in October, you found out that you won a MacArthur Genius Grant. This is this incredible honor. And I'm curious, not the math yet, but just emotionally, what did it feel like to find this out? And especially, you were the only mathematician among the 22 winners. So what did that feel like to represent math in this way?
So it was a very strange and surreal experience. I want to mention that the backstory is that back in May of 2025, essentially all the federal math and science grants at Harvard were canceled. I had a NSF individual grant for my research, and I had 2 NSF conference grants, and they were just terminated in one fell swoop in May, which was incredibly stressful, in part because I was organizing a conference at Harvard the first week of June, and I was using a conference grant to do so. And so to all of a sudden have the funding yanked out from underneath us was very, very stressful. And then in the months that followed, I would say that I and most of my colleagues were quite demoralized. It felt like higher education and scientific research were at this period of existential crisis. Still feels like that way, by the way. But then in the fall, I got this call from the MacArthur Foundation saying that I had been awarded this grant, and it was just this shock, this amazing gift, which first of all told me that somebody cared about my research after all, and second, that I would have the funding to be able to keep doing the work that I was doing. So it was an incredible gift, and it couldn't have come at a better time.
And did you know you were in the running, or was this completely out of the blue?
No, it was completely out of the blue. The way things work is that they're done by anonymous nomination. So I have no idea, I had no idea that I was being considered.
Now, let's back this up a little bit more. When you joined Harvard faculty several years ago, you were one of the only women in the department. How did you decide to come to Harvard, and what was that like?
So it was a shock to me when I learned that Harvard was wanted to hire me. This was back around 2016 or so. I guess maybe I'll preface that by saying that I myself was a Harvard undergraduate some years ago, and it was at a time when there were no women math professors. And I had an amazing time as a student. I loved my friends. I loved my classes. I really felt at home there. I didn't want my time to end. But it was just a fact that there were no women math professors, and there never would be, or as in my own mind, it felt like there never would be. At the time, I wanted very much to eventually become a math professor somewhere. I didn't know if it was going to work out anywhere, and I certainly could not have imagined at the time that I would wind up back at Harvard. And then when I got this call from Harvard, I guess around 2016 or so, it was this kind of surreal experience. And at the time, there were no women in the math department. And so that was also a kind of a scary thing to imagine, being perhaps the only one there. But I guess a couple things a couple things went into my decision. So at the time, I was at Berkeley. I was tenured at Berkeley. I loved being there. Berkeley is a fantastic department, fantastic place to live. But one of the ways in which I tried to decide what to do was to view the question through the lens of where could I do more good. And at Berkeley, I felt I was reaching many students. I was teaching classes with over 200 students sometimes. I was reaching a very wide demographic, lots of students coming from all kinds of backgrounds. And then I knew coming to Harvard, I would be teaching much smaller classes consisting of students that, generally speaking, came from much more privilege. But on the other hand, I knew that being a woman in the department might make a difference to some of the students there. So that was one of the things that I was trying to weigh. I did worry a little bit about how it would feel to be the only woman in the department. But when I visited Harvard, my colleagues were incredibly welcoming. They really made my gender not an issue. And I'd had experience in the past, being in situations with very few or no other girls or women. I'd been at a summer camp in high school, the Math Olympiad program, where I spent 1 month as one of 24 students and the only girl. That was an extremely stressful experience, but having gotten through that with my sanity intact, I felt like, being in a department where I was the only woman would be fine. And so, like I said, my colleagues were incredibly gracious. And then a few years after I joined, we hired 2 more just amazing women mathematicians, Melanie Wood and Laura DeMarco. So now it just feels like a non-issue to me.
That's fantastic. And I love that the detail that the challenges you faced earlier ended up really helping you, that, you grew through the adversity. And I think there's an important lesson there.
Yeah.
So speaking of challenges, one challenge that a lot of mathematicians face is solving really hard problems. And let's take a chance to turn over to your research. So broadly speaking, you work in combinatorics. And let's just start by saying, what the heck is that?
So I would say I work in algebraic combinatorics, and algebra is things like polynomials, and combinatorics is the study of discrete or finite structures. Sometimes in combinatorics, one solves, tries to solve some kind of counting problem, maybe about an object from algebra or geometry. So one of the first things that I studied in my PhD was an object called the positive Grassmannian, which is it's a geometric object. There's the Grassmannian of k-planes in n space, which is the space of k-dimensional subspaces of an n-dimensional vector space. When k is 1 and n is 3, you can imagine the set of all lines going through the origin in 3 space. And then there's also a notion of positive Grassmannian, which is the set of k-planes with some kind of positive property. So this object was actually invented/discovered in the late 1990s and early 2000s by George Lustig and Alex Posmakoff independently. And when I was a graduate student at MIT, the first question that I worked on was trying to solve a counting problem about the positive Grassmannian. And I can say, as an analogy, if you think about a 3-dimensional cube, then you could, if you're a combinatorialist, you would look at a cube and say, okay, well, there's 6 2-dimensional square faces, and there are 12 one-dimensional edges, and there are 8 zero-dimensional vertices. And so these numbers, 6, 12, 8, are numbers we can associate to the cube. Now, as I mentioned, there are infinitely many positive Grassmannians, and their dimension can be arbitrarily high, but just like a cube, they can be decomposed into pieces of different dimensions. And so my first problem was to find a formula for how many pieces there were of each dimension for each positive Grassmannian. And so I wound up writing down an explicit formula for that.
Now, there are some unexpected applications outside of mathematics with that, if I remember correctly. Can you tell us about that?
Yeah, that's right. So about a year after I wrote my first paper on the positive Grassmannian, I saw a paper by another mathematician, Sylvie Courtil, who I didn't know, but her paper said that the polynomials that I introduced to count the cells in the positive Grassmannian, that these polynomials actually represented probabilities in a model from statistical mechanics called the asymmetric simple exclusion process. And this model, asymmetric simple exclusion process, this was being used as a model for translation in protein synthesis and also as a model for traffic on a one-way street. And so to me, it was just totally wild that these polynomials that I thought, just counted cells in the positive Grassmannian but had nothing to do with the real world, actually were saying something about probabilities having to do with traffic flow and translation and protein synthesis.
That's amazing. Do you have without going into the mathematical details of why, do you have a philosophical reason why this one object is so ubiquitous?
Somehow in mathematics, subspaces are so important. Linear algebra, the study of subspaces, the study of all subspaces is so universal that I guess it's not surprising that it would have to do with other subjects. But I don't really have a great explanation for that. I mean, I did, in years after that first connection, other connections were found between the positive Grassmannian and other fields of math and physics, just completely different and also kind of wild connections. So it's something that I've observed, but I don't really have a good philosophical reason why this happens.
I guess that's part of the fun is you don't know where these bridges will show up and where they'll lead, so you can explore and it's an adventure.
Yeah, that's right.
Okay, so when we're reading a research paper, we get this kind of cleansed view of research, right? There's definitions and theorem statements and references to the literature, but there's no explanation of the human side of how the research happened. So given that we have you here on this very human-focused show, can you tell us some examples of times when you're doing research when you really were reminded that you're a human, not just a machine?
Yeah, absolutely. I have some fun stories about that. So in fact, after I saw this paper of Sylvie Courtille linking my polynomials to the asymmetric simple exclusion process, I got excited about studying the asymmetric exclusion process, and I started trying to prove a better, more refined version of the theorem she'd proved already. So I was working on that, and I found something cool. I wrote a paper, I made it public, I put it on the archive, and I sent it to her. And then she and I emailed back and forth a little bit. And I remember, and I didn't know her at all, but in an email, she complained about being pregnant. But anyway, so we had some math chit chat. And then one day I got a message from her saying, "I'm very big and slow, but here are some thoughts." And there was this 1-page LaTeX manuscript, and it just had an idea for how to generalize the theorem that I had proved. And as soon as I saw her conjecture generalization, I knew my proof was going to go through. It was going to prove this more general statement as well. And so I excitedly wrote back to her. I said, "How about I'm going to update my paper? I will add you as co-author." And I thought, this should be, a nice deal for her. She doesn't have to do any writing. She gets her name added. And but then I didn't hear back for 1 day, 2 days, 3 days. And finally, at the end of that 3rd day, I got an email from her with one word, "Yes," and a baby photo. And so our first paper basically coincided with the birth of her son. And then, 9 years later, we were working on another paper together, Sylvie Courtille and I. And it was while I was pregnant with my son. And we were sort of editing the paper, polishing it near the end of my pregnancy. And one morning I woke up and I thought, I feel a little different. I think I better get this paper out there. And so I sort of quickly did a last round of revision, and I put the paper on the archive. This is the mathematical repository for math papers. And I went into labor that night. And then a few days later, I shared a kind of silly announcement with some friends that was jointly announcing the birth and vital statistics for both my human baby and my math baby.
Fantastic. I won't ask which took more than 9 months.
They both took 9 months.
Another note. You have another project going on here. All you see on Twitter and the New York Times, and you have a team called First Proof. So let's learn why you started that and why you undertook it.
So our First Proof project is meant as a way to come up with an objective assessment of the ability of AI systems to provide mathematical proofs to specified statements. And we had a few reasons to start this. I mean, one is that in the media, you see so much hype, pro-AI hype, anti-AI hype, and it's hard to know what to believe. There's hype saying that AI can, do everything mathematicians can do. It'll solve math. And there's hype saying, AI is going to be the end of the world and humans as we know it. And a lot of this information being put out there is by people who who have skin in the game. Maybe they work for a company or, that sort of thing. And so we thought it would be best if mathematicians who don't have a conflict of interest, who are not working for or consulting with AI companies, if we take it upon ourselves to try to come up with an assessment of how good is AI at doing mathematical proofs. I do want to mention one other thing before I go into the details, which is that, the work of mathematicians is more than just proving statements. We have to come up with the idea for the statement. We have to come up with a conjecture or come up with the right definition or come up with the right framework for solving the problem. So in a sense, proving a mathematical statement is only sort of one part of the puzzle, but it's the only part that we felt we could test. So then it came to trying to devise a test. How do you determine how good an AI system is at coming up with a mathematical proof? It's actually tricky to test this because AI models are so good at searching the internet that if you ask an AI model a problem and the solution is somewhere on the internet, it'll just find it. And so we had to come up with problems whose solutions were not on the internet. And so what we did was come up with problems from our own research that we had recently solved but had not made public the solutions. So in the end, between the group of us, we came up with 10 problems, different areas of math. We came from, different universities around the US, a few international as well. And we put out a document called First Proof, which contained these 10 problems. That was February 6th, Euler Day. And we, at the same time, had written up and encrypted our own solutions to the problems. And we made these encrypted solutions public just to show we had solved them and also to guard against the situation that, say, AI scoops us, right, on our research. So we encrypted these problems. We made public. So we encrypted the solutions. We made public the problems, and then we said we will release the solutions in 1 week, and which was basically like midnight at the beginning of like February 14. And so during that week, there was this incredible flurry of activity. AI companies jumped in, a lot of professional mathematicians tried, math aficionados also tried, students, people, because basically we were inviting anyone who wanted to take our problems and give them to their favorite AI model and see what happens. And so it was this experiment, this sort of data gathering week, or several weeks really, for us to see what happened and try to figure out best practices for testing AI models and prepare for our next more formal round of problems.
So what resulted from this? I can imagine there was, and I saw a little bit of this on X, for instance, there was a lot of attempted and purported solutions. So I can imagine on your side, you're probably deluged with dozens, maybe hundreds of, let's say it, AI slop, things that look mathy, that look like they might be solutions, that likely most of them have problems, but some of them don't. So how do you deal with that? I mean, where do you go?
That's right. So we did try to make very clear when we put out this paper that this was going to be an experiment, and we weren't thinking of it as a formal benchmark, and we didn't have the capacity to formally grade solutions. I mean, that didn't stop people from sending us, solution after solution after solution, but we did try to make it clear that we weren't going to be formally grading them. But let's see. One takeaway was that it is very hard for almost anyone to determine whether a solution produced by AI is correct or not. I had some very smart students, give me a kind of a solution set. They thought that with the AI models, they had solved maybe 5 out of the 10, and they'd gotten AI to write up the solutions in this beautiful looking manuscript, 45 pages, sent it my way. And I just took a look at the solutions produced for my problem. And even though they look polished, they're written with an air of confidence, they were just completely wrong. And so, so there was a lot of that. There were some of the AI companies did produce some correct solutions, but again, one of the reasons we said we weren't going to call this a formal benchmark or do rigorous grading was because we didn't put out any ground rules for the competition for this round of problems. We didn't say, for example, we didn't set out a protocol for testing. And mathematicians who have used AI know There's a big difference between the results you'll get if you say, give AI one shot to answer a question, or if you're a mathematician who goes back and forth and has an extended dialogue with AI. And so, of course, many of the solutions produced may well have been a back and forth between an expert mathematician and an AI, but we just didn't know. We didn't have any protocols. We didn't have any particular rules, and so we've refrained from making any kind of formal assessments. Just because if you sort of if you sort of put out a problem set, but don't say whether don't say what are the rules surrounding collaboration or tools, then it's a little bit meaningless to comment on results.
I have to point out a humorous irony that's striking me here. In our classroom teaching, cheating is when the students use an AI when they're not supposed to. In your benchmark or your test, cheating is when the AI is using a human when it's not supposed to.
That's right. Because we really, in this case, we want to test the capabilities of AI as opposed to the collaborative ability of AI plus human. But
Fascinating,
that's a funny point.
That is true, but I'll let our listeners unpack that as they wish.
Now, the big question with this is what happens next?
That's right. So we've actually been really, really busy gearing up for what happens next. So this Saturday on Pi Day, we're going to make an announcement regarding the second round of problems. So we will have a second round of problems, and this time we do intend to do formal assessments. So we're going to lay out what is the protocol, and we're also going to actually assess the solutions. So we've been talking to people at AI companies to come to an agreement, and we know a few things. We again want one of the rules to be that it's going to be a sort of a one shot, AI gets one shot to answer the question. Again, because we just don't know how to separate the ability of AI from a human if a human has a back and forth with AI. But yeah, so this Saturday, we're going to have the announcement of the second round on our webpage with more details. And also this Saturday, several of us will be going to New York to be part of a panel discussion at the Museum of Math exactly about the ability of AI to take part in, to produce proofs of mathematical statements. And so for anybody who's going to be in New York this Saturday, it'll be at 6:30 p.m. at the Museum of Math.
So, Lauren, you mentioned in high school you were the only girl in this high school math camp. When you won this Genius Grant just recently, you're the only mathematician. When you started at Harvard, you're the only woman in the faculty in the math department. So you've been through a lot of interesting experiences that I think were probably exciting and challenging in different ways. Do you have any advice you could share to a young person, maybe a young girl in particular, who might be thinking about what their life will be like if they continue in math?
Yes. My advice probably is not really specific to gender, but I would say that people should keep in mind that math and a career in math research is a marathon, not a sprint. So I would tell people, don't worry about what everybody else is doing. It doesn't matter if somebody seems quicker than you, if they seem to know more than you. I think as long as you love math and you have the determination, you're going to make it work. So really to try to tune out the rest of the world and just focus on what you can control. Another thing I would say to young people is that, well, to anybody really, is I think it's really important to be kind and respectful to the people around you. And of course, one, because it's just the right thing to do. But two, I would say the world of math is so small that, if you stay in math research, and when you're 30 or 40 or 50 or 60, you're still going to be seeing some of the people that are in your cohort right now, who are students with you right now, or your peers, or wherever you are. You're going to remember, and they're going to remember, who was a jerk and who was kind and supportive and uplifting. So I would just encourage people to try to be kind and respectful to everyone around them.
Now, is there anything else that you want to share with our listeners?
One thing I would say for someone who is maybe starting a career in math research is to look for mentors wherever you can. And, if you're a woman, of course, it's great to have a female mentor, but male mentors can be fantastic also. And it's great to have a a mentor who's in your own department, but you can also find mentors outside of your department. So I would just say look for mentors and friends and community wherever you can. And I've been really fortunate to have, over the course of my life and career, really probably hundreds of amazing teachers and mentors and friends who have guided me and inspired me.
That was Lauren Williams, professor of mathematics at Harvard University and a 2025 MacArthur Fellow. Today we talked about how abstract mathematics can lead to unexpected conditions. We also explored one of the biggest questions facing the field right now: what role artificial intelligence might play in the future of mathematical discovery. If you've enjoyed this conversation, share it with someone who thinks that math only lives in textbooks, because Lauren's work shows mathematics often appears in places we least expect it. So until next time, stay curious and stay informed of the world around you.